The second approach in the bracketing method is the Newton-Raphson method, and in this method actually the derivative information of the equation is used to approach the root. And you know, the derivative is actually a tangent. You can see here, let's say we have the initial point xi and the function fxi, and the tangent of it at this point is this, and this tangent shows a direction for the next iteration point. So it is extrapolated down to the x-axis from the point xi fxi. From here it is extrapolated towards the x-axis on the path of the tangent, and the point where this tangent crosses the x-axis is an improved estimate of the root. And basically this Newton-Raphson method actually has the derivative information. That's why from this slope over here of the tangent, we can just have the tangent angle of this side divided by this side, and from there we can get a formulation. So what we can do is the tangent or the derivative fxi is equivalent to the vertical distance and divided by horizontal distance. That means fxi minus 0 divided by xi minus xi plus 1. So this one divided by this one. And if we isolate xi plus 1, because we don't know this actually, we isolate it here, then xi plus 1 is equivalent to xi minus fxi divided by fxi derivative. So this is the Newton-Raphson formula, and as you can see, this includes the derivative information here and the function information here and the initial point. So this Newton-Raphson is actually derived from the Taylor series expansion as well. So you can check the book for the proof of it, but we are not going to show it. We are just showing the formula based on the geometric interpretation of the tangent. So the Newton-Raphson is quadratically convergent, and if you consider the Taylor expansion, if we have only the first derivative, then starting from the second derivative, it is the error. So in the error also we can truncate after the second derivative, then we can have actually an error information based on the second derivative. So that's why it's quadratically. So there is a square over here. It means quadratic error decrease, let's say, and that's why we can represent the error as like e square, and that's why the error is roughly proportional to the square of the previous error. So you can see it is like quadratically reducing, let's say, in terms of error. And if we compare with bisection, which is reducing linearly, half or less than half, this is much more reduction at each iteration, which easily finds the final position of the root. And this tangent direction gives a great information to quickly go there. We have an example for Newton-Raphson method, example 6.3, and in here we are using the same example that we used for bisection, and we want to actually estimate its root, which is the true root is 0.5671, and we want to estimate this using the Newton-Raphson method. And over here you see the iterations, but I will use some calculations to find the initial iterations actually. So to be able to use the Newton-Raphson method, we need to find the derivative of the function, because we need, if you remember, the Newton-Raphson was xi plus 1 is equivalent to xi minus fxi divided by f derivative xi. So we need this function. We have this function, but we don't know this. So we can find actually fxi using the actual function here and taking the derivative. Then if we take the derivative of this, it is minus e minus x minus 1. So this is x is I, basically. Then we can simply use this here, also this here, and modify this as our Newton-Raphson formula specific to this one. So then xi plus 1 is equivalent to xi minus e minus xi minus x divided by minus e minus xi minus 1, like this. So this is our formula for Newton-Raphson. Then we can start substituting the initial gas here and start from there. So let's say over here you see I is equivalent to 0, then x0 is equivalent to 0, then xi plus 1 becomes x1 actually equals, this is x0. Then we will write, if x0 is 0, minus exi over here is actually e minus 0 minus 0 divided by minus e minus 0 minus 1. And in here you can see that this is 1 and this is 1 as well. So that it becomes actually 1 divided by 2. So this becomes 2. This is 1. That's why it's 1 divided by 2. And minuses are becoming positive. That means x1 is 0.5. And we can calculate this easily. So here you can see for I0 it's 0 and for 1 it's 0.5. And the true error here is 100% because the actual value is 1 for x equals 0, and 1 minus this gives the true error. Let's calculate the true error. Epsilon t is equivalent to x0 minus the true root 0.56714329 divided by 0.56714329. It's about 100, let's say, over here. Then for 0.5, now we are at I equals 1, then x1 is 0.5 and x2, we can calculate x2, but let's calculate epsilon t for x1. So this was 0. X1 is, so actually this is directly 100. X1 is 0.5 minus 0.56714339 true value divided by the true value. Actually you can use, because you will not know the true value, you will simply use the approximated error, the error between the previous and current iteration. But for now we are just calculating it because the book calculated this. So here 0.5 minus 0.56 and it gives us 11.8. Here 11.8%. And when we go to I equals 1, x1 is 0.5 and x2 is simply here again, now x2, this is x1. X1 is, we said, 0.5 minus e to the power, let's erase this, e to the power minus 0.5 minus 0.5 divided by e to the power minus 0.5 minus 1. And from here, the result is 0.556631103. Then we can calculate ET as x2 minus 0.5674329 divided by 0.5671439, and the result here is this one. So 0.147%. You can see it's quickly it converts to a very low value. So it is like quadratic reduction in the error. This is clearly seen. And we got this result. Then you can continue actually. x2, I equals 2. And I equals 3. And I equals 4. You can do the same calculations and find these. And you can also calculate ET. ET is just the top part of this. Let me show. This is actually ET, and this is also. These are capital ET. Oh, sorry. This is, let's erase this and use the regular pen. This is ET. Maybe ET0, ET1, ET2 over here. So you can calculate these easily and have the ratio and the regular ET. And you can see it's a quadratic reduction. It's a very fast reduction. And after the fourth iteration, it's really quick, as you can see. If you compare this with bisection, in the bisection, it was very slow. Let's check the error in the Newton-Raphson method. And when we check the error formula, if you remember, this was the formula with the quadratic values and the second derivative. So let's try to solve it for this example again, for example 6.3. And again, the first derivative was f derivative x is equivalent to e minus x minus x. Now we need also the second derivative, because here we have the first derivative, but here we have the second derivative. And let me write it down in blue. In the second derivative is coming from this, but the first derivative was actually 1. Let me write 1 here, and minus actually. So this is minus ex, yes, this one. Now from here we can have the second derivative. It is actually positive e. It becomes with minus and minus multiplication, minus x, and minus 1 becomes 0 in the second derivative. And this is just the second derivative. And by using these, we can simply calculate our error. And the error is, let's start with maybe I equals 0. But instead of that, we can just simply write these into the equation and find the formulation. Et I plus 1 is equivalent to minus second derivative ex minus x divided by 2 times minus e minus x minus 1, like this. And also there is eti square. We simply use this part here, you can see. And from here, if we have some corrections or some simplifications over here, we can have but we need to say that x, when we use the true value of x, so x true is equivalent to 0.56714329. If we use this, let's write this way. For this one, eti plus 1 is equivalent to, when we put this here to the x and here to the x, we obtain this value. I will just be quick and write the final result. 0.18095 e squared ti. So here we have this value, and we can simply use this for the 0th iteration. For example, let's say I is 0, then et1 is equivalent to 0.18095 et0 square. And what is et0 square is? Actually, we know that this is, for example 3, this was 0.56714329 in example 6.3. So when we substitute this here, simply et1 becomes almost 0.0582. And if we compare this with the true error in the previous slide, the true error that we found from the calculations, it's close to that, close to the true error. ET1. Let's write the true error like this, or maybe this is like the estimation only, because this is just an estimation. Let me just clear this and make it this way. This is the estimation, and the true error ET1 is equivalent to 0.0671439. You can check example 6.3 to see this value. These are very close. You can see the magnitude are similar, but of course there is some differences, and the differences are getting closer when we continue. If I equals 1, for example, ET, not I, but here it's 1, so ET1, here 2 is equivalent to, simply we will put now 0.8095 ET1 square. For the next iteration, we simply put this here, then ET2 is equivalent to 0.0008158, and the true error ET2 from the previous slide, from example 6.3, was 0.0008328. Of course, when you put the error you found for the previous slide, you will get a very close result, you can see. But if you continue with the approximated error, maybe putting this here will change this a little bit more, but still will be closer. So this is a good enough result, close enough. So this error basically is the estimation of the error, and we can simply use that this way. And if E equals 2, then E3, the estimation is 0.1895 times, again here now, ET2 square, we will put this here, then it's very small actually, 0.000000125, and this is exactly the same. ET, this is the estimate, not estimation. This is not estimation. This is the regular ET, and ET3 is equivalent to, again, this 6 zeros 125. Same. So we are getting closer to the error with the increased iterations. When we use this, we can have a good calculation of this value, actually, the error. As we come closer to the root, we can much better calculate the error. That's the command that we can make here. And the Newton-Raphson method error prediction is actually proportional by a factor of square of the root of the error, let's say. So it's getting smaller in terms of like a error square amount, let's say. So it's quartering the error and reducing it.